Hey guys, it's Malta here, and in today's video, we're going to learn how to evaluate the continuity of a function. Many of the strategies that we will discuss are based upon key ideas from Algebra 2. However, our previous knowledge of limits will also prove to be useful in some problems. So without any further ado, let's get into it. So with this first problem here, we're being asked just to describe and discuss the continuity of the function. And so it's very nice because we've been provided with the graph of the function. And so when looking at this graph, there's two, areas or points that I want you to immediately look at. And the first is that x equals -2. And so I want to look over at x equals -2 because, as you can see, there's these blue dashed lines that we have. And these blue dashed lines, what these mean is that we have a vertical asymptote present. And a vertical asymptote is going to be a point at which we have a non-removable discontinuity. And that's going to be important because we're trying to describe the continuity of this function. Now, similarly, over here at x equals 2, this blue dashed line appears again, and it's symbolizing that there is a vertical asymptote with some non-removable discontinuity. So with this function, as you can see, our only points of discontinuity are at x equals -2 and x equals 2. And so for that reason, the way that we can answer this question is we say that this function is continuous other than x equals -2 and x equals 2. So there we go. Alright, so then for this next question here, it's very similar. We have, once again, the graph of the function is being provided, and so that'll make our life much easier. But in this case, before I actually jump into the solving part of the continuity, I want to just examine this piece of the function here, this x that has these two bars surrounding it. And so I just want to describe what this means. And when we have these two bars around this x variable, this means that there is that we're dealing with a greatest integer function, or as some people like to call it, a step function. And so what this means is that wherever we have an integer, we're going to see that there's a jump discontinuity, there's a step. And so you can see that here throughout integers -1, 0, and 1. We're always making a step. It's always a step upwards as we go from left to right. And so this is important because this is a non-removable discontinuity. And so in this case, as you can see, we have these straight lines here, which are all continuous, but then we have this jump at the integer. And so our only spots of discontinuity are at these integer values. And so the way we answer this is we say that there's just discontinuity at every integer. So there we go. That's all we got to do for this one. Alright, so for this one here, what we're being asked to do is we're trying to discuss the continuity of the function, but we don't have the graph anymore. And so for us to figure this one out here, what we got to do is we got to figure out where are we going to have a discontinuity present. And so what we're dealing with is we have the square root. We have the square root of 49 minus x squared. And so as square roots, our issue for discontinuity is when the value inside the square root becomes negative. And in that case, we're dealing with complex numbers. But for our sake, we're just looking at real numbers. And so if we have a negative value, that's going to indicate that this function's undefined at that point, and that's a bit of a problem. So we got to figure out where is this value in the square root going to be negative. And so the way that we'll do this is we'll say 0 equals the square root of 49 minus x squared. Because this right here, when we solve this equation, this x value that we get will tell us, okay, if we have an x value of some number, we're going to get 0. So then we know that we're very close to where this breaking point is, that this value under the square root becomes negative, and that's what we want to find. So in order to solve this, all that we got to do is first we're just going to square both sides. So 0 squared is 0, that's nice. If we square the square root, we just get 49 minus x squared. Now it's just simple algebra. We can move the x squared over, and we get x squared equals 49. Alright, from here, we gotta take the square root of both sides. So we're just gonna get x equals the square root of 49. And then all that we say is x is gonna be equal to plus or minus 7. So what this value here means is that at 7 and negative 7, we're going to get a value of 0 when we put that into 49 minus x squared. And so what we got to do now is we got to figure out, okay, where is this value, 49 minus x squared, going to be negative? And so the way we're going to do that is we're going to say, okay, what if we went up a value and we went to positive 8 and negative 8? So if we went to positive 8, we're going to get 49 minus, and then in parentheses, 8 squared. So then this is going to end up giving us a value of a square root of negative 15. And that's really good because guess what? We've just discovered that at 8, guess what? We have a negative 15 value in our square root, and that's going to yield an answer of undefined. So we know that if we get above this positive 7 value, we're going to be undefined. Now what we're going to do is we can go the same way here, except we'll do it with negative 8. So we get 49 minus negative 8 squared, and once again this is going to yield a result of negative 15. So what we can say is, at least in our instance, we're good inside this interval from negative 7 to 7. It's once we get to beyond that range that we end up facing some discontinuity. So we can say for our answer here that we are continuous within the negative 7 to 7 interval. And that's all that we need to say. So there we go. We're continuous within the negative 7 to 7 interval. Alright, so our next question here, we're dealing with the same thing. They want us to discuss the continuity. And so in this case, we're dealing with a bit of a piecewise function. And you know that because guess what? There's one function up here, and then there's a function down here. And look, this one's only applicable at x being less than or equal to 0. This one's only applicable when x is greater than 0. So the piecewise, what we're going to do is we got to look and see, where is there going to be discontinuity? And the discontinuity in this sort of piecewise, because it is linear, is going to be where they, are supposed to match up. So where x is equal to 0. And the interval actually for this one, I forgot to include this, is negative 1 to 4. So there we go. Alright, so to begin with, let's just try and figure out how this will work. So if we say 3 minus 0 in parentheses, because remember we want f of 0. So if we want f of 0, we're going to say 3 minus 0, alright, so then f of 0 equals 3. Okay, that's great. Now for the other function, we're going to do the same thing. F of 0 of that function, that's 3 plus 1/2 times 0. Alright, so then we get f of 0 equals 3 once again. So that's great because look, they match up. And that means that we're going to have no discontinuity over the course of this interval because look, this is a linear line, this is a linear line. There'd be no breaks throughout, throughout their path. And so therefore we can say because there's no break at this x equals 0 part where they meet up, there's going to be no discontinuity at all. So pretty much there's no discontinuity. So this is continuous over the interval. Alright, so here's our next question. So once again, we're going to be looking at the continuity of the function, discussing it, trying to find any places of discontinuity. So in this case here, we got this g of x equals 1 over x squared minus 4. And so if we're going to look for discontinuity here, because we got this fraction, we're going to try and see where this denominator is going to equal 0, because that's going to yield an answer of undefined. So if we say x squared minus 4 equals 0, we get x squared equals 4, and then x is going to equal the square root of 4, and x is going to equal plus or minus 2. Now, in this case, the negative 2 is not important because look, that's beyond our interval. That's too far negative. But the 2 is important because the 2 is within our interval here. This interval, we see it's got closed brackets on both sides. That means we're inclusive from -1 to 2. And so the problem is, at 2 we got a discontinuity, because at 2 we're going to have, at g of 2, we're going to have this being 1 over 0, which is undefined, and that's a discontinuity right there. So what this means here is that we are not continuous over this interval. And so all that we got to say is, we can say simply that not continuous at x equals 2, because it is undefined. So that's all we got to do, is we just got to say, look, within the interval we have a problem at -2 and +2, but look, +2 is included within the interval, and so as a result it cannot be continuous over the course of the interval. Alright, so for our next question here, we're looking at finding points of discontinuity within this function. So we have f of x equals 6 over x. And as we did with our previous question, because this is a fraction, we're going to try and see where is x going to be 0. Now this is pretty easy, I must admit, because it's just x all alone in the denominator. So all that we got to say is, well, for x to equal 0, well, x has to equal 0. So we can flat out say that, yeah, there's going to be discontinuity at x equals 0. That's no surprise. Now, one thing we're going to have to do, though, is we got to figure out, okay, we know there's discontinuity at x equals 0, but what type of discontinuity is it? Is it removable discontinuity, or is it non-removable discontinuity? And so this is where our limits become pretty important. So what we're going to say is, we're going to say the limit as x goes to 0 of 6 over x. And so that's just going to become 6 over 0. And I'll put that in parentheses because we're replacing the variable. So if we evaluate this limit, what we're going to get, once again here, is that we have a value that's undefined. And so because when we're trying to evaluate the limit, we got a value that's undefined, we know that this is not a removable discontinuity. If it was a whole, guess what? We would have gotten a value, but we didn't get a value. So obviously we know that we have a bit of an issue. We know that this is a non-removable discontinuity. So all that we have to say is, a limit does not exist at x equals 0. So there is a non-removable discontinuity. So that's all I gotta say. So a limit does not exist at x equals 0, so there is a non-removable discontinuity present. In this next question here, oops, that's a copy over. In this next question here, we're looking at 4 over x minus 6. Once again, we're trying to figure out any areas of discontinuity. So once again, we want to figure out where is this denominator going to be equal to 0. So the way that we do this is we say 0 equals x minus 6. Alright, we get x equals 6. So at x equals 6, we're going to have some discontinuity, but we don't know what yet. So what we're going to say is, we're going to say the limit as x goes to 6 of 4 over x minus 6. And so what this is going to end up getting us is we're going to get 4 over, in parentheses, 6 minus 6, which is going to yield a result of 4 over 0, which, as we know, is undefined. So once again, what we can say is a limit does not exist at x equals 6, so there is non-removable discontinuity. Alright, so there we go. So this next question here, we're looking at f of x equals x squared minus 9. So in this case, this one's pretty easy, just because of the fact that this is a parabola, and as we know from parabolas, they're going to be continuous throughout. There's no area at which they'd ever not be continuous. So with this one, it's pretty simple, and all that we got to say is, well, it's a parabola, and all that we answer is we say it's a parabola that will be continuous from negative infinity to positive infinity. So a parabola that will be continuous for all values of x. It doesn't matter if I put in, let's say, negative a million or a million. It's always going to result in a value, and it's always going to be continuous because it is a parabola. So we don't have to do really anything for this problem at all, which is pretty nice. So for this next problem here, it might not look too similar to the last one because we now have this coefficient with this x variable, and we didn't have an x variable previously, but once again, our highest degree is to the second power, so we know that this is a parabola. And as we did with the last problem, we know that parabolas are always continuous. This one is no different. So all that we got to do is we say, well, parabola, if I can write parabola, that would be nice. So we say it's a parabola, continuous for all values of x. Alright, so there we go. That's all we got to say. Alright, so in this next question here, it's going to get a little bit more complicated with figuring out our discontinuity. So we got f of x equals x plus 2 all over x squared minus 3x minus 10. So in this case, what we want to do, we're dealing with a fraction, so we want to figure out, hey, we're going to make this denominator equal to 0. So all that we got to do is we say 0 equals x squared minus 3x minus 10. And then if you factor this, what you'll get is you get 0 equals x plus 2 times x minus 5. And so then what we can do is you just got to say 0 equals x plus 2. So then x equals negative 2. Alright, that's the first part. Then we say 0 equals x minus 5. Alright, x equals 5. So we know right away that at negative 2 and at 5, we have some discontinuity. But once again, we got to figure out where is the discontinuity. So there's actually two methods through which we can actually solve this. The first is we can look and see if there are holes present, if at one of these values there is a hole. And so the way that you determine if there is a hole is we're going to try and reduce this original function. So this function really is just f of x equals x plus 2 all over x plus 2 times x minus 5. And so the reason why we know this part, the reason why I know that this is a factor of the denominator as well, we just did that previously. So we just put this back in here because x plus 2 times x minus 5 gives us x squared minus 3x minus 10. So we just factored it down. Now looking at this, as you can probably tell, we have this x plus 2, this common factor of x plus 2. So we can knock this out of the numerator and knock this out of the denominator. Now this is really important because of the fact that we can knock both of these out. We know that at x plus 2, when we set that equal to 0, we know that when x equals negative 2, this is going to be a hole because of the fact that we can just simply chop this out. We can remove this common factor from the numerator and the denominator. We know that at x plus 2 equals 0, there is a hole present, so then at x equals negative 2, if you simplify it, you get that there is a hole. Now I will say this, if you don't want to do it that way, you can still go with the method of using it with a limit. So all that you got to do if you want to use this with a limit is all you got to say is, okay, we really have, once you simplify again, we really just have f of x equals 1 over x minus 5. Alright, now we're going for a limit. So what we'll say is the limit as x goes to negative 2, we're looking for the limit as x goes to negative 2 of 1 over x minus 5. So what we're going to do for that is we're just going to say we're going to get 1 over negative 2 minus 5, which is going to end up getting us a result of negative 1 over 7. So as you can see, a limit exists. And so because a limit exists at negative 1 over 7, we know that this is a removable discontinuity. If it was non-removable, we wouldn't get a limit. Now let's check out 5 really fast here. So with 5, as you can see, unfortunately this whole test doesn't work too well because we can't prove it's a whole. There's no common factor that can knock it out in the numerator. So let's just immediately go to our limit test. So with our limit test in this case, we're just going to say we're going to have this f of x, again, equals 1 over x minus 5. And then we're going to we have the limit as x goes to 5 of 1 over x minus 5. So let's do our substitution. We get 1 over, then parentheses 5 minus 5. That yields a result of 1 over 0, which is, well, undefined. And so we cannot find a limit at x equals 5. And you know what that tells us? That there is a non-removable discontinuity. So basically the way that we're going to answer this question is we're going to say there's a removable discontinuity at x equals negative 2. And then at the same time, we say there's a non-removable discontinuity at x equals 5. So there we go. That's all that you got to do to answer this question. So as you can see, knowing our limits ended up proving to be very helpful for figuring this one out. Alright, so for our next question here, we're looking at this, I guess, absolute value function that you can tell because we have these absolute value signs around this x plus 7. And so I know for a lot of people this will instantly cause some fear because, it's absolute value and that's a pain to deal with. But hey, we can solve this just as we've worked through and solved the other fraction problems. So what we want to do is, with the fraction, we know that it's going to have, a discontinuity if we get the denominator to be equal to 0. We don't have to worry about the absolute value in the numerator because absolute value functions, those are always continuous. They have a cusp, mind you, but a cusp is still continuous. That's still a point of continuity. So all that we got to do is we got to check out where this x plus 7 in the denominator is going to equal 0. So what we do is we say 0 equals x plus 7. And then we get x is equal to negative 7. So we know here, right off the bat, that at x equals negative 7, we're going to have some sort of discontinuity. Now, what we're going to do actually is we're going to rewrite this function a little bit. Because this function is really x plus 7 over x plus 7. When, or I should say if, x is greater than negative 7. Because if it's greater than negative 7, guess what? This absolute value has absolutely no purpose. If we're, let's say, at 0, 0 plus 7 is just 7. And 0 plus 7 with the absolute value is still 7. So essentially, the absolute value doesn't even exist if x is greater than negative 7. So what this means here is that we can just say that then x plus 7 over x plus 7, that's just going to be equal to 1. So that's equal to 1, if x is greater than 7. Or if x is greater than negative 7. Now on the flip side, we can also rewrite this as being negative of x plus 7, negative of x plus 7 over x plus 7 if x is less than negative 7. Because if x is less than negative 7, like if it's negative 8, we get negative 8 plus 7, that's negative 1. Well, we need the absolute value in this case to get it back to a positive 1. So the absolute value is in effect. But we can really just, in a sense, do the exact same job as the absolute value by putting a negative out here. Because if we say negative 8 plus 7, that's negative 1, well, the negative of a negative 1 gives us 1 again. So we've essentially done the job of the absolute value with just this negative sign out here. So what we're going to do is then this is going to end up giving us a result of -1 if x is less than -7. So obviously, if x is greater than -7, we're at 1. If x is less than -7, we're at -1, which definitely tells you that, hey, at -7, we got a bit of a problem, which we already identified earlier. But because we have this jump from, let's say, -1 to 1, we know that we are dealing with a non-removable discontinuity. So we can say here simply that there's a non-removable discontinuity at x equals -7. So that's all that we gotta do. Simply put, with this absolute value, we just gotta turn it into, I guess it's pieces, in the sense of, okay, if x is greater than -7, guess what? We don't even need the absolute value. Hey, if x is less than -7, we're gonna need to put a negative, out front of this numerator to replace the job of the absolute value. And then as you can see, we had this jump here from -1 to 1, which is why it's non-removable, because jumps are always a non-removable discontinuity. Alright, so with that taken care of, we have another one here, which is this one. We have 3x squared when x is greater than or equal to 1, and ax minus 4 when x is less than 1. Now, with this sort of question, we're being asked, what value do we need to make a in order to have this be continuous? So what I like to do is I like to say, okay, first we got to figure out what value do we need this ax minus 4 to equal when we're at 1. And we know we're looking at 1 because, look, 1 is where we have this meeting point. It's where the merger's happening. So we got to make sure that at x x is 1, that at 3x squared when x is 1, that we have the same value as ax minus 4 when x is 1. So to begin with, what we're going to say is, okay, so if we have f of 1 of 3 times 1 squared, that's just going to give us f of 1 equals 3. So this is our meeting point at 1. So we got to be at 1 comma 3. And so what that means is we got to say ax minus 4 has to be equal to 3. So we get ax is equal to 7. And from here, all that we got to say is then we know that we're looking when x equals 1, because that's where our meeting point is. So all that we got to do is we got to say we have a times 1 equals 7, so then a equals 7. And there we go. We figured out that, hey, we got to look when a is equal to 7. Alright. For this next question here, we have a very similar problem. It's the same thing. We just got to figure out what is going to be our value of this variable a to make sure that this is continuous. So for this part here, we're going to say f of 2 is equal to 2 cubed, because the 2 just goes into here to replace this x variable in x cubed, and we get f of 2 is equal to 8. So we know 8 is our meeting y coordinate. So 2 comma 8 is where we want to meet up. So what we got to do is we got to say, okay, we got to say that a x squared has to be equal to 8. And so what we're going to do is then we can say we have a times 2 squared, because we're looking at x coordinate of 2 is equal to 8. So we get a times 4, or 4a, is equal to 8. And then we get to say that a is equal to 2. So that's all that we got to do for that question. And, there we go, we've solved it. So a is equal to 2. And when a is equal to 2, we're able to make sure that this piecewise function is entirely continuous, which is pretty important. Alright, for this next one here, it's a little bit tricky in the sense of we now have 3 piecewise functions that we're dealing with, but this isn't going to be that hard. We just got to do it in stages and we'll be fine. So our first part here is we got to say that our first meeting point is that x equals -1. It's our first meeting point. Then our second one is that x equals 3. So what we're going to do is we'll say f of -1 is equal to 2, because that's what we see up here. Whenever x is, -1 or under, we're 2. So f of -1 equals 2. And that's important for us because then all that we can say is also we can say that f of 3 equals 2. Because look, whenever we're at or greater than 3, we're at, I should say, my bad, -2. We're at -2 over here. So what we got to do is we got to say, we're going to be looking at, we have ax plus b equals 2 when x equals -1, and ax plus b equals -2 when x equals 3. So now all that we got to do is we pretty much are just going to say this. We're going to say we have a times -1 plus b equals 2. And then we're going to end up getting -a plus b equals 2. And so from here, what we can say is this is our one part here. And then our next part is we say we have a times 3 plus b is equal to -2. And then we get that 3a plus b is equal to -2. And then all that we got to say is we now have these two distinct equations here. All that we did here is we said, look, our x coordinate is at -1, and we got to be equal to 2. So then all that we did was I simplified this. We did the same thing over here. Our x coordinate is at 3, so we put the 3 in for x. Guess what? We got to be equal to -2, so we set that equal to -2 like so. Then all that we got to end up doing is we say, okay, if we have -a plus b equals 2, then b is just going to be equal to a plus 2. And so we're just going to practice some substitution. So the other part that we have is we have 3a plus b equals -2. So with substitution, all that we get to do is we say 3a plus a plus 2 is equal to -2. And this results in us getting 4a plus 2 is equal to -2. And then we get 4a equals -4, and a equals -1. So there we go. We just simply did some substitution. Now we just got to figure out b. So to figure out b, all that we got to do is we have negative of -1 plus b equals 2. So all that we do is that ends up being 1 plus b equals 2. So then b is equal to 1. So there we go. A is equal to -1 and b is equal to 1. That's your answer. Alright. For this next question here, we're actually looking at, it's a little interesting, but we're looking at a composite function. And so we're trying to put these parts together. And so what this is going to involve for us is we're going to we have like h of x equals f of g of x. So let me just write this on screen. We're looking at a composite function of h of x equals f of g of x, like so. And so we're going to want to make this composite function and then determine its continuity. So for this, what we're going to do here is we're going to say h of x in this case is equal to, if we put g of x, which is x minus 1, and replace it for this x and x squared, we're going to get x minus 1 squared. And that is, well, that's a parabola. So we know right there that, well, this is going to be continuous from negative infinity to positive infinity. So all that we got to do is we got to say parabola continuous for all x. And that's all we got to do. Now, in this next question, we have something very similar. We're doing the exact same thing. So we're looking at h of x equals f of g of x, like this. And so we want to first figure out what h of x is going to be. So h of x in this case is just going to be equal to 1 over x squared plus 5 parentheses minus 6. And so the way that we did this was we said, okay, look, we have to put our g of x, which is x squared plus 5. We got to replace that into this x variable in 1 over x minus 6. So we end up getting 1 over x squared plus 5 minus 6. So all that we got to do is this simplifies down to as h of x equals 1 over x squared minus 1. So there we go. Now what we can do is, if we want to find discontinuity with a fraction, we know we're going to be looking at this denominator to be equal to 0. So all that we do is we say 0 equals x squared minus 1. And then what ends up happening is we get 1 equals x squared. And then we get that x equals plus or minus 1. So right there we know that we're going to have discontinuity at 1 and negative 1 with this composite function. Now to determine if it's non-removable or removable, we're going to use our limit test again. So what we'll say is we have the limit as x goes to 1 of 1 over x squared minus 1, or you can call this the limit as x goes to 1 of 1 over x plus 1 times x minus 1. And so what's going to happen in this case is, regardless of which one we put in, we're going to get 1 over 0 if we put 1 in for that variable x. So regardless, we're going to get 1 over 0, which is equal to undefined. So we know right off the bat that that there is a non-removable discontinuity at x equals 1. Discontinuity at x equals 1. Alright, now it's time to perform the exact same test, but at x equals negative 1. So let's say the limit as x goes to negative 1 of 1 over x squared minus 1. So we get that, or the limit as x goes to negative 1 of 1 over x plus 1 times x minus 1, like this. Draw this out. And then what will happen is, in this case, once again, we're going to get 1 over 0 if we just do this substitution where we put the negative 1 in for our x variables. And this is undefined. And so once again, we just say that there is a non-removable discontinuity at x equals negative 1. So that's all we got to say. So yeah, so thanks for watching. I hope this was pretty helpful. We're just solving and trying to figure out continuity. And so really it comes down to trying to identify where are the areas of discontinuity. And so a lot of this stuff I know is, material from Algebra 2. So hopefully this was a good review from your Algebra 2 days. But regardless, I hope you enjoyed the video, and if you liked it, give it a like, and if you want to see more content like this, be sure to subscribe. So see you next time, and